So let's do a couple of design examples. In this first design, we have a robot with an arm, and I've, on the photo is one of the robot arms that I've constructed. It has 4 degrees of freedom, but the example that I'm going to do here, I'm only going to do the calculations in 1 degree of freedom. So what we have on the diagram, the circle represents our motor, and it's going to lift the 5 kilogram load. So this is our requirement. And there's another one of the robots that I've constructed. So what we want to do is actually move that using a 500 millimeter arm. And so we start off by looking at what motor has been supplied. And the problem is this motor good enough for the job to lift that load? So the solution, we calculate the force required to lift that load, and force equals MA, so 5 multiplied by the gravitational acceleration, 9.81 meters a second squared, is 49.05 newtons. And we then convert that into the torque over the 0.5 meters, and we end up with 24.5 Newton meters. So immediately you can see that our motor is far too underrated to lift that weight. So the conclusion, we can't lift it. And we can either shorten the arm or choose a motor with a higher torque. In the second example, we're going to look at this robot and determine the speed, torque, electrical power, current, and battery capacity, and recommend the wheel type and how long our battery will last. The parameters are that the motor chassis is 400 millimeters, the speed is 1.2 meters a second, and our payload, that is the weight of our robot, is 200 milligrams. We're going to drive 2 wheels, and it will be on all of these surfaces, marble, wooden floors, or carpet. And we'll use a removable lithium battery, which has a 900 milliamp hour capacity. Looks like this, and you can see that next to the computer mounted on the motion base. Okay, so we'll start off calculating the friction of our surfaces, and the formula for doing that, the force of the friction, is mu times n, where n is the weight of the robot, and it's a product of the mass and the acceleration due to gravity. Mu is our coefficient of friction, and we can do that by looking up tables of what those coefficients are. And for marble, it's 0.4, and for wood, it's 0.2, and for carpet, it's 0.7. So we'll use those in our calculations to calculate the friction. So N is 200 milligrams times 9.8, 2.16 newtons. And our friction, as a result of that, we multiply it by 0.7 to get 1.51 newtons. And now we're going to look at the acceleration when we move our robot. So we're assuming we'll start off at 0 speed, and we want a design speed of 1.2 meters a second within 5 seconds. So the calculation of that ends up with MA. So we've got 0.0528 newtons. And that contributes with our friction to give us the total force of 1.562 newtons. Now we have to select the tyre and the wheel. Not a lot of choice here because we're going to use Lego Technique components and Lego wheels and tyres. So we want to make sure that our tyres give us a good traction on all the surfaces that we've chosen. So we'll use soft rubber tyres. It has a good grip on all the surfaces. And the wheel diameter, well, we've selected a Lego wheel that has 35 millimeters radius. And that gives us a pretty good compromise. Okay, so we select the DC motor, and the torque on that is provided by force by radius, the radius being the 35 millimeters of our wheel. So the torque is going to be 1.5 newtons times the radius, and we end up with a torque of 0.0273 Newton meters. We'll adopt a safety factor and increase that by 2. So we end up with 0.0547. And our design speed, when we consider the radius of the wheel and the speed, ends up at a rotational speed of 327.4 revs a minute. So what we're going to use is a battery. So while it's a LiPo battery of 3.1 volts, it does have a step-up voltage for the motor of 5 volts. And taking our calculations so far of torque and speed, we then calculate the power by multiplying the two of these. And that gives us a total torque, since we've got two motors, of 3.75 watts for our power. And since we've got 5 volts, our current is going to be 0.75 amps. And for our 900 milliamp hour battery, we can last 72 minutes. And that's our second design example. So in summary, what I've reviewed in this video are the understanding the principles of rotary motion of a DC motor. And I've related those to the electrical power and other electrical parameters. And I've used electric motors on a number of my robot projects, and I've demonstrated how I've done that. And I've also given a couple of examples, design examples, where the electrical and mechanical properties of robots are used in design. And here are some of my references.